Hello everybody. Let's get started. My name is Asier Gutierrez. I work for Huawei. I'm a software engineer. We do mainly the lab I'm working for. We do Linux stuff. We are mostly interested in memory management. We do some scheduling and some stuff. I'm going to show you a couple of techniques that we try to use to detect hot applications, how we can improve the memory management by hot applications. I'm going to divide this talk into two topics, two blocks, explaining two different approaches that we took. Sorry. For whatever reason doesn't work. Yeah, here you go. That's a very stupid slide. You probably already know. Linux, we use virtual memory addresses. Well, tasks use virtual memory addresses who need to be translated to physical memory addresses. We use a page table to do that. Usually, modern processors for a long time, they have this TLB or which stands for transaction local-site buffer. And the CPU will always hit the TLB first. So if we miss, we walk through a page table to get the actual translation page. Otherwise, we use the one from the TLB. On the right-hand side, you have pretty much how it works. So you have like the gray box is in one core. And the kind of yellowish block is like a shared among all the cores in the processor. Again, but this depends on the platform. So this happens to be like the one I looked into. Okay. So as I mentioned before, TLB, transaction local site buffer. Usually you have one per core. Is part of the MMU. You usually have, nowadays like two-level TLB, L1 and L2. This is like the cache in the processors. Second-level TLB usually has prefetching. The problem that we have with TLB, and this has been like a really bottleneck, a serious bottleneck in production, is the TLB size, which is very, very limited. So I have there an example of, I got this from the internet. So from an AMD Zen 5 processor, that's like up to 12 channels with a total of 6 terabytes of memory. And still the I and D TLB L1 is like 6496 entries. For I and D TLB level 2 is like 2048, 4096 entries. So what we see is like the amount of memory available in servers right now, it increases a lot faster than the TLB size, which means that, eventually we will have more TLB misses, and this will slow down translations. There is a way, a workaround that, and that's the use of huge pages. So these, instead of using 4K, usual 4K pages, we can use 2 megabyte or up to 1 gigabyte of page size. The real advantage, as you may know, is like bigger page size. You can pack more stuff, which means less translations, which means less TLB misses. Now, Linux has these two implementations of huge pages, so a huge TLBFS and transparent huge pages, or THP. We'll try to focus this talk specifically on THP, transparent. So what we actually wanted from the beginning is to have some kind of translation that can be transparent to the user. So the user doesn't need to allocate anything, and a lot easier way. Okay, just an example. This is like a server I got my hands on. It's like a very old Intel Xeon Haswell server. But as you can see, this server has had, I think it's over 100 gigabytes of memory, but still you can see like this 64 data DTLB entries, like 4K, up to 1024 entries for L2, so it's like very, very, very limited. Okay, so that's very, very nice, but the problem is nobody uses huge pages. Nobody uses it for these reasons that you see over there. Latency spikes, so when you introduce transparent huge pages, you will find compaction, you will find page migration, and you will find page collapses. These can happen, well, randomly or well at any time. So the sysadmin has no control, almost no control on those. The other big problem is memory waste, fragmentation. So you have there like an example of 3 blocks. Fragmentation always happens, right, with 4K pages as well. The problem is fragmentation is a lot higher with 2 megabyte or 1 gigabyte pages. Increased fragmentation, both external and internal fragmentation. And this means that eventually if you run a server for significant amount of time, and most production servers run for a long time, you will run into a situation where you run out of memory. So you run out of memory, out of memory execution, kills a process, and so on. So that's why most guides for user applications, for most sysadmins disable transparent huge pages. So we have these three modes in Linux for THP, never always a name advice. So sysadmins always try to use never, because it's like they don't want to deal with the problem that the server, for whatever reason, just runs out of memory in a month. Okay. Couple of real cases we look into at Huawei. So the first one, the one on the left, is bare metal server with database. In our case, we were testing MySQL. It could be PostgreSQL, Oracle, whatever. And we wanted to use only huge pages for that database, and not for the entire server. The other one on the right is even more interesting, and this is a cloud environment. So nowadays everybody uses Kubernetes and container orchestration systems. And we may have a situation where we want a particular pod in Kubernetes to use huge pages, but we don't want the rest to use them. So we look into this, and well, this our proposal that we submitted. There was quite interesting feedback from the community. So our proposal is very simple. We try to use THP inside C groups. So to assign different THP policies to different C groups. Has the advantage that we can group a number of a number of tasks under the same C group. It has the advantage of can be easily integrated into Kubernetes and Docker. And the way we do it is just with lazy huge page collapsing. So this is like the K huge page D thread in the Linux. We just add a slot there, and it will just collapse eventually, asynchronously. Okay, so when we started looking at this, how we could use C groups and how we can improve TLB performance, these were the open questions we had. So we wanted, first of all, we wanted to be able to group tasks under the same policy. We wanted something to be transparent. So we wanted to keep that thing of transparent huge pages. The customer or the user doesn't need to set anything strange. We wanted to easily integrate into cloud environment, and what we wanted also is just to be able to split applications. So the hot applications, give them huge pages. The cold applications, leave them alone and just keep using 4K regular pages. Okay, so a little bit about C groups. What you have on the right is like container. All those mount, hostname, PID, and so on, those are namespaces. Taking like a normal LXC container technology, so I'm not gonna get into hypervisors. What you see is that just the inner yellow part, that's the C group. So the C group is between the application and the other namespaces. So a C group allows us, that's actually how Kubernetes and Docker works. It uses C group to limit the amount of memory, processors that can be used by a particular container and so on. C groups are used for resource management. I know that, we shouldn't do this because, it's quite of memory management. Is it really a resource? So this is like quite controversial part, but that's the only mechanism that Linux kernel right now has to group different tasks under the same, group. So the other thing about C groups, it has a hierarchy. So there is a root, you have children, and those children will inherit the stuff from the parent. Okay, so this is our approach. How we initially, the suggestion that we made to the community. So we have these two new files added to the C group: memory THP defrag and memory THP enable. They use the same kind of methodology as the normal THP settings. So you have always an advisor never. And what you can see there is we created a new group called THP group. We added a task with PID 089 to that C group. We enabled THP for that C group, as always. And after some time, we see like some collapse happen, like 2 megabytes are used as huge page. You can see that in SMAPs. So, very simple. Our approach was based on Linux kernel 6.11. Not much change, so last 500 lines of code, pretty simple. Okay, so I try to remove all that stuff that is irrelevant here. I try to just show you the most relevant piece of code from the div. So what you see in huge memory, which is the part that allocates memory, in our case we call on the left on the THP VMA allowable orders, we call a new function, memcg THP VMA allowable orders, which is on the right. This function, which is part of the C group stuff, mem control, which deals with memory management in C group. What you see is just if we first check if that task belongs to a C group. If it belongs, we find which memory order we need to get, and we just return that. It's very simple. It's not rocket science or anything. Okay, so, I have the slides there on sched.com, so you can check. You can also check the patches that were submitted if you're interested. some benchmarks. Well, this is the server that I mentioned before that I got my hands on, like the Haswell server, like a very old server. I tested this with MySQL 8.0. I know it's an old version of MySQL, but at least to find out, like a basic figures. We use sysbench, and what we see on the left-hand side is like the transactions per second for MySQL. The beginning, when MySQL runs on very few cores, so it's like 6, 10 cores, it is worse without a patch, but otherwise it's almost the same. In some cases, when we have like a lot of cores used by MySQL, our approach is a little bit faster. On the right-hand side, you see the actual huge page consumption by the server. So what you see is like MySQL, we set it to always. It will automatically start collapsing stuff, and it will use a lot of memory. So it's like 3 gigabytes. When we use C groups only for MySQL, we see I think it was from 800 up to 800 megabytes of huge page consumption. So a big difference over there. And this is just like a server using MySQL and running like all sysbench on the same server. So we didn't have anything else. But for whatever reason, Linux decided to collapse a lot of stuff when using always. Okay, so problem that we have. As I mentioned, a C group, it uses a hierarchy. The problem is what happens when you have 2 C groups like here with different THP policies, one with always, the other one with never. What do you set in the root? This is like an open question. We don't have an answer. We were told by the maintainers that unfortunately this proposal actually breaks C group consistency. I completely agree with that. Well, we kind of gave like a potential way around that, which is to use something like huge TLB does. So, or something like when you allocate memory. You can use memory limits in C group as well. You can use huge TLB limits as well. So in this case, you can set to 8 gigabytes, well, a little bit more than 8 gigabytes to THP group, right? We could do the same with our solution. Okay. The other problem is this solution means that sysadmins and DevOps will have to change scripts, deployments, and so on and so forth. There was this concern by the community that adding new knobs to C group may actually pollute C groups. So what we may end up is, if they accept this patch over here, they may end up like in 6 months somebody submits another patch with another knob for C groups. In 10 years we may have like 100 knobs, and that will be unworkable by sysadmins. As Jonathan mentioned before his talk, there is a problem that Linux is very conservative. They don't want to add stuff that needs to be maintained afterwards, and it may cause pain to users. So, well, that's one of the approaches. I'm going to finish here the blog. This blog. This is one of the approaches we had. So we look into a different approach, which is the use of daemon. Okay, so here's the thing. Even if we allocate THP to a particular task, that task may have hot areas in the memory space, and it may have cold areas as well. So It doesn't make sense to collapse the entire memory space for a task, especially if the task uses a lot of memory. So we look into something called DAMON, which stands for Data Access Monitor. It was added into a Linux kernel like a few years ago, I think. So it's very simple. It divides the memory into different regions. It keeps track of those regions. And it can detect hot and cold regions. It's relatively lightweight, so I got this from the developer that came up with Damon. There is around 1.5% degradation, so it's not that much. And there are two ways you can interact with Damon. So one is through sysfs, the other one is a set of scripts that the guy that did Damon published as well. This is like user space scripts in Python mainly that changes like some settings in sysfs. Okay. Simple concepts about Damon. It can monitor either physical or virtual memory. It will use kthread, so it will just launch a new kthread kdamon, called kdamon, for each scheme. And each scheme in Damon can have a certain actions to be applied. So there's like stat, collect stat, collapse into huge pages, page out, and so on. There are quotas. Quotas is like a time frame or just some such set of limits, because the idea is that some actions may take quite some time to be performed. So to limit and to stop that when it takes too much time and too much memory. Watermarks, when Damon can be activated or deactivated. Filters and access patterns, which is the most interesting part. You can set when these actions will be applied, right? When a region size reaches a certain size, when we have a certain amount of access numbers to that region, age, and so on. So, okay. Basically, what I try is to condensate what you see in sysfs when trying to figure out and use Damon. So you have the one context. It can be set to physical address, virtual address, or VPADDR is just like a range of virtual addresses. So it's just not the entire virtual address space for that process. Then you have, well, you see there up to scheme N. If you look at the code in Damon, unfortunately right now it only supports one scheme. The guy said that we'll just work on supporting multiple schemes. And you have all the stuff that I mentioned before, access patterns, quotas, actions, and so on and so forth. Okay, so how does Damon work? It's very simple. It performs a binary search. It basically, as I mentioned before, divides the memory space into regions, reset the access bit in the page table after some time, rechecks the access bit in the page table, and eventually just like merges, splits memory regions to try to find like the hot regions. Not rocket science. Now, Damon has a very interesting stuff. So some of the kernel functions are exported, which means that you can effectively create a Linux kernel module which can control Damon. It can activate it, deactivate it. This kernel module has access to exported functions in the Linux kernel as well. So we can have like a module that can interact with user space, with part of the kernel space, and control Damon. Okay. Again, I try Okay, this is the thread that is spawned by Damon, the K thread, the kernel thread. I tried to remove a lot of the stuff. The most interesting stuff is that, like these red lines. So you see prepare access check. It will just pick up a random. It will go through all the regions in that we are scanning. It will pick a random address in those regions, reset the access bin, store that in the context, then we'll sleep for some time, that's the interval, and then we will check those access bits in the page table. And you have the apply scheme. The apply scheme will just check whether the action is eligible to be used. One main thing to mention is that Damon uses virtual and physical memory addresses. So when we do prepare access check, we reset basically the access bit in the translation table. If we use physical table, prepare access check will just do reverse mapping. Through reverse mapping, we will find the task and the task that belongs to that memory address, and just reset the correct virtual memory address in the translation table. Okay. Now, Damon has a very interesting. I mentioned like the user space tool that Damon has. It has a way to get these flame graphs as well, which is very interesting from when you're trying to analyze a program from user space, something that doesn't make sense or you want to optimize. We took those scripts, we slightly changed it. We didn't do anything like really difficult. We, instead of getting like a kind of entire frame graph from the entire task, what we did is we split the flame graph into many flame graphs, one per VMA. So what you see there is this MySQL. This is how Damon sees MySQL. This is the heap actually for Damon, around 24 megabytes. And you see that most of them is just not used. So it's used like the upper, 4 megabytes, maybe 5. So this give us an idea of, where we need to collapse the stuff. Okay. So we thought, okay, maybe we could use this Damon to actually try to effectively collapse and huge pages. So we slightly modified Damon that is used in the vanilla kernel. We modify it to perform partial collapses. So when we, for example, collapse this heap, we will not collapse the entire address space, but just collapse, obviously with alignment, but collapse the part that is heavily used. Now the problem with Damon is, to apply the actions, there are some access patterns. Those access patterns, the most interesting part is like the minimum amount of memory accesses per region to trigger that action. Now, if that amount of memory accesses is too high, what we will end up is like wasting CPU cycles, because Damon will just run and effectively do nothing, because now the bar is set too high. On the other hand, if we set it too low, we may end up just collapsing stuff that we may not want to collapse. So ideally, we wanted to have some kind of dynamic mechanism to find the amount of accesses needed for a collapse to happen. So we work in a module that I hope we will release in the open source soon. I mean, we haven't, it's quite buggy at the moment, so we don't have anything stable to release yet. But we created a module. What you see there on the left and the right is just the same, different ways of expressing the same algorithm. But we created a module that sets really high minimum amount of accesses for that region and checks if any collapse happened. If it doesn't happen, you would just slowly lower the amount of memory accesses until a collapse happens. At that time, it will just stop there. No, and it will stop just lowering the memory accesses. It will just let Damo keep working on the background. This will happen. This loop happens like around every 5 seconds, something like that. So should be, in our benchmarks, it was more or less okay. Okay. What we have is this. There is a problem. As I mentioned before, with Damon, you need to mention the user space that you want to check. So you need to give him the PIN. Again, this is not something that we really wanted it. We wanted something like more transparent. So just the person loads, for example, our module, that's it. And he forgets about, the module will find by itself which applications are hot and which not. So what we thought is like, okay, we will try to find the top 3 applications by U-time, by user time. So we use the same as calc load. Is an exponential moving average. It's used by top. So if you run top and you see like these 3 numbers over there, it uses calc load. The loads that you see when you run top, it will just use from the scheduler, like how much each processor is used actually by actual task, right? What we wanted is to do something really similar, but use the U-time, the user time per task. And we picked the 3 tasks, the most used tasks, and we run a daemon thread for each one of them. For the ones that turn cold, so before they were really hot and now they turn cold, we just stop this daemon thread. So this is pretty much the same as I just said. We get the delta. So this loop is like 5 seconds again. We get the delta. We calculate the exponential moving average for all the tasks. Pick the first 3 tasks. If they don't have a daemon running on them, we launch them. And we just stop daemon for any other applications that we were running before that now are cold or are not that hot. Sorry. For a reason just doesn't work. Okay. We did some benchmarking. Our setup, again, Linux kernel 6.11, MySQL, this time a little more updated version of MySQL. This server, sorry, I just forgot to mention here in this slide, it was running an ARM processor with 4 NUMA nodes. We just pinned MySQL to one of the NUMA nodes to try to avoid any cross NUMA traffic, and these are the results we got. So this is the same as before, so transactions per second versus threads used by MySQL. And what you see is like, well, you have there like 3 lines for 2 megabyte always for this daemon with partial collapse that I mentioned, and the regular like 4K page size. And as you can see, we are performing a little bit better, not that much, but it's like maybe from between 1 and 2% better than 4K page size. Our module with Damon with partial collapsing also outperforms always in terms of transactions per second. This is the same as before. So memory consumption, this is huge page consumption, and consumption RSS, like the entire consumption for that task. So again, we compare like always against Damon, and again, memory consumption is a lot lower for our case. Okay, one thing, if we go back to my first slide when I talk about TLB and so on, I mentioned about the thing about TLB hits and TLB misses and so on. We went to the performance counters for this ARM processor. We tried to find out whether our hypothesis was correct or not. It turns out that yes, performance, so DTLB misses are lower now than were before with 4K. And the same thing for instruction TLB. In fact, with instruction TLB, as you can see, we have like a more flattish line, like the yellow line, instead of those spikes. So, well, this is the end of it. Like two different approaches. The first one is like we release the comments on the Linux kernel community. We got some feedback from them. I know that people have like similar approaches, but using eBPF and launchers and so on. This other approach we have with Damon, hope we can release any pretty soon as well into open source. And we hope that we can actually combine both and come up with a really interesting way to speed up memory accesses and lower TLB misses. So, I don't know, questions? Yeah?
My question is about the grouping. In my opinion, all you need is flat grouping rather than hierarchy characteristics C group has, right? So I think it's just a file that list of the process that need THP.
Mm-hmm.
I think it's enough for your purpose. But is there any problem if you use the A file for listing of the process that need?
Yes, so the question is about grouping, like maybe instead of having like a hierarchical mechanism like C groups, we have something like flat. Yeah, you're right. We look into different possibilities. So one is like the one I mentioned, using limits that would keep C group hierarchy consistency. The other one is like adding something to proc, for example.
Yeah, proc file system?
Yeah, adding something to proc file system where we could just set this.
I think it's sufficient to...
Sorry?
I think that is sufficient to achieve your goal.
Yeah. This is something that we actually thought. We haven't implemented it yet. The question is like, how would Kubernetes use this?
But I think, I'm not sure, but if it, inheritance between parent and child, and using that, I think it can work even with Kubernetes. No.
Well, if we use like limits, as I mentioned before, that would work fine with Kubernetes, because Kubernetes, Docker, Containerd, and so on, they use C groups. So this is how they set, for example, limits to particular pods and containers. You can probably integrate this a lot easier. But yeah, I mean, your suggestion is this is just another suggestion how to fix this problem, because unfortunately a lot of people are having problems with huge pages. Yeah.
I understand.
Yeah.
It's for easy iteration
Yeah.
with Kubernetes, because that is already based on C group.
Yeah, sort of. So that was our idea was like, okay, we want if you look at, well, we're running out of time, but no, but yes, just very quickly. The problem that we have in the Linux community is like Linux kernels, they work on the kernel, but they don't work on the user space. User space, if you talk, for example, to Kubernetes guys, they will say, okay, we are glad to add this feature, but we don't have the kernel support for that. And sometimes you need to bridge both ends.
Thank you.
So, yeah.
Have you done any benchmark performance testing that is showing in the end of the slide?
Yeah.
Done against the AMD EPIC, the Gen 5 processor?
No, we just received like I know a couple of weeks ago a server with AMD Zen 5. We haven't tried it. Yeah.
Yeah, because I saw it
Yeah.
in the earlier slide.
Yeah. You know, just.
But you expect that it will be the same benefit?
Yeah, I mean we tested this on Intel servers, Xeon. We tested this on ARM. We saw very similar results, so not much difference. Yeah.
What's the group stuff? What's your exit strategy of a task from a C group that has enabled huge pages to the one that does not have any?
Okay, so the question is like the exit strategy when a process leaves the C group or just dies or whatever. Okay, so what we did is we during the attachment of a process to a C group, we just apply the policy for that C group when you attach a process, right? So it will collapse and so on. When you detach, it will just the slots that were added to K-thread. There were, I mean, the slots that were added for collapsing. Those slots remain there. So this is one of the things we haven't worked. When you detach, we don't split those memories. We did this for a simple reason, that the splitting is actually a fairly expensive task. So
you can have process that belong to C group that does not have huge pages, but they use huge pages.
Yeah, you can have that, yeah. You can eventually, if you change from one C group to another one and so on, you may end up with those situations, yeah. Okay, I think, thanks a lot for being here, and any feedback, please go ahead. Thank you.